Okay, we're going to go through the circular motion in-class problems number 1. So we're taking driving the car around a flat curve, so it's not a banked curve. I'll look at it from above, going in the direction v this way, and being pulled into the center here. So my acceleration is towards the middle. We know the coefficient, we know the speed. The best way to draw this force diagram is to look from the side, like the car is driving into the page or out of the page. So the normal force is supporting the car, and then static friction is pulling to the inside. I don't know if it's at its maximum or not, or at least I don't know that it's at its maximum. So I can't call it mu sub Sn. Direction of positive towards the center of the circle is always a good idea. So F net y, n minus mg, those have to balance because my acceleration needs to be just towards the middle of the circle. This is circular motion here, so I know that the a is either v squared over r or 4 pi squared r over delta t squared. I'm going to use v squared over r because that's what I know. And so really I don't have to do any algebra here because I know all these numbers. So if the 1300 is, yeah, it's just that expression there. So I'll plug in the numbers now. 1300 kilograms, 16 meters per second. We have to square it over the radius of the curve, 59 meters. And that gives us 5,640-ish newtons. It's a pretty large force, but if you think of it in terms of the weight, it's a 1,300 kilogram car, so the weight is 13,000 newtons. It's quite a bit less than that, and we know the static friction force can get up to almost 90% of that 13,000 newtons, so it's definitely within the realm of the possible. Now if we want the maximum speed, now we can say that the static friction force is at its maximum value. So I can say that F sub s is mu sub s n. The vertical dimension didn't change, so I can substitute from that mg equals n, and I can cancel there. I'm looking for the v, so I'll move the r over and take the square root, and this will give me almost 23 meters per second, which is getting close to 50 miles an hour. So if we're taking this curve at maximum speed, that means we can't ask any more of the friction force. If I were to slow down or speed up, I would, in addition to this acceleration that I need for turning, I would also need some acceleration parallel to me, which means that the total acceleration is greater. So the net force needed is greater, so we're asking more from the static friction force. That's not actually a good plan. I mean, if we could get slower, that would solve the problem, but if we're already at the speed, we can't actually slow down. If I did turn the steering wheel towards the outside of the curve, what that does is increase r, which gives me a smaller acceleration and gives me, that extra room I need to speed up or slow down if I want to do that. Turning it towards the inside of the curve would reduce r and increase my acceleration. That wouldn't work either.